What if something no bigger than a city could shut down satellites, wipe out electronics, and tear atoms apart from thousands of light years away? Not with explosions, not with fire, but with pure invisible force, no warning, no sound, just raw power spreading silently through space. This is not science fiction. This is real, and it already exists in our universe. Meet the magnetar. At first glance, a magnetar does not look dangerous. It does not swallow stars like a black hole. It does not shine brightly like a supernova. Most of the time, it sits quietly in the darkness, spinning slowly, almost forgotten. But that calm is misleading. A magnetar is one of the most violent objects ever discovered. It is a cosmic monster that hides its strength until the moment it releases it. A magnetar is born from the death of a massive star. When that star collapses, it leaves behind a crushed core so dense that matter itself is pushed beyond normal limits. But in rare cases, something even more extreme happens. The newborn neutron star gains a magnetic field so powerful that it bends the rules of physics. This magnetic field is not just strong, it is the strongest magnetic field known to exist anywhere in the universe. To understand how powerful this is, imagine the strongest magnet on Earth. Now imagine something 1 trillion times stronger. A magnetar's magnetic field is so intense that it can stretch atoms, distort empty space, and crack the solid crust of the star itself. These cracks, called starquakes, release more energy in a fraction of a second than the sun produces in hundreds of thousands of years. In some ways, magnetars are even scarier than black holes. A black hole needs to be close to harm you. You have to fall into it. A magnetar does not need to touch you. From across the galaxy, a single violent flare from a magnetar could damage satellites, disrupt communication systems, and flood space with deadly radiation. And the most unsettling part is that magnetars do this without warning. They do not roar before they strike. They do not glow brightly to announce danger. They stay quiet, invisible, waiting. Yet magnetars are not villains. They are natural creations of the universe, shaped by the same laws that created stars, planets, and life itself. By studying them, scientists are learning how matter behaves at its absolute limits. Magnetars push gravity, magnetism, and energy to extremes we cannot recreate on Earth. They act like cosmic laboratories, revealing secrets about reality that no experiment ever could. In this video, we're going to explore magnetars step by step, without complicated math or confusing terms. We will see how they are born, how their magnetic power works, why they crack and explode, and what would happen if one came too close to Earth. We will separate science from fear and facts from fiction. By the end, you will understand why magnetars are not just powerful objects in space, but reminders of how strange and astonishing our universe truly is. A magnetar is one of the strangest objects ever discovered in the universe, and understanding it begins with letting go of what we normally think a star is. When most people hear the word star, they imagine something bright, warm, and life-giving, like our sun hanging calmly in the sky. A magnetar is the complete opposite of that image. It does not shine to support life. It does not burn fuel peacefully for billions of years. Instead, a magnetar is the crushed, violent remains of a star that has already died, leaving behind an object so extreme that it pushes nature to its limits. At its core, a magnetar is a type of neutron star. That means it is born when a very massive star reaches the end of its life. For millions of years, that star burns fuel in its core, balancing gravity with energy. But when the fuel runs out, gravity wins. The star collapses inward at incredible speed, triggering a massive explosion known as a supernova. What remains after this explosion is not always the same. Sometimes the core becomes a black hole, sometimes it becomes a neutron star, and in very rare cases, it becomes something even more unusual, a magnetar. So what is a magnetar really? In the simplest terms, a magnetar is an ultra-dense, ultra-small object with an unimaginably powerful magnetic field. That magnetic field is the defining feature. It is what separates magnetars from all other objects in space. Everything a magnetar does, every burst it releases, every crack on its surface, is driven by magnetism. A magnetar is not a normal star because it does not produce energy through nuclear fusion. Normal stars shine because atoms are being fused together in their cores, releasing heat and light. Magnetars have no such process. Their energy does not come from burning fuel. Instead, it comes from stored magnetic energy. Think of a magnetar like a tightly wound spring. It does not move much most of the time, but when it releases even a small part of its stored energy, the result is violent and sudden. One of the most shocking things about magnetars is their size. Despite being among the most powerful objects in the universe, they are incredibly small. A typical magnetar is only about 20 kilometers across. That is roughly the size of a large city. You could drive across it in less than an hour. And yet this city-sized object contains more mass than our Sun, which is more than 1 million times larger in volume. This alone makes magnetars hard to imagine. Our brains are not built to understand how something so small can be so heavy. To help picture this, imagine taking the mass of the Sun and compressing it into a sphere the size of a city. Gravity crushes everything inward so tightly that atoms can no longer exist in their normal form. Electrons are forced into protons, creating neutrons. That is why neutron stars, including magnetars, are made almost entirely of neutrons. The result is matter packed so densely that a single teaspoon of it would weigh billions of tons on Earth. No mountain could support it, no container could hold it. It would fall through the planet like a ghost, pulled straight to the center by gravity. This extreme density is another reason magnetars are not normal stars. Normal stars are soft and gaseous. Magnetars are solid, rigid, and incredibly hard. Their surface is often described as a crust, similar in concept to Earth's crust, but unimaginably stronger. Even so, this crust is constantly under stress. Why? Because of the magnetar's magnetic field. The magnetic field of a magnetar is the strongest known magnetic field in the entire universe. It is so powerful that it deserves special attention, because without understanding this magnetism, you cannot understand magnetars at all. Earth has a magnetic field that protects us from harmful radiation and allows compasses to work. The Sun has a stronger magnetic field, which drives sunspots and solar flares. Neutron stars have even stronger magnetic fields. But magnetars go far beyond all of these. A magnetar's magnetic field can be trillions of times stronger than Earth's. This number is so large that it almost loses meaning. Instead of focusing on the number itself, it helps to focus on the effects. Near a magnetar, magnetic forces are so intense that they can physically distort atoms. They can stretch them into strange shapes, breaking the normal balance between particles. Even empty space is affected. Quantum effects appear that do not happen under normal conditions. In a very real sense, the magnetic field of a magnetar reshapes reality around it. This extreme magnetism is why scientists call magnetars the most powerful objects known. Power here does not mean size or brightness. It means how much energy is concentrated into a small space. A magnetar stores an enormous amount of energy in its magnetic field. When that energy is released, even for a fraction of a second, it produces some of the most intense bursts ever observed in space. Despite all this power, magnetars are usually quiet. Most of the time, they do not emit large amounts of energy. They spin slowly, sometimes taking several seconds to complete one rotation. From far away, they can appear calm and inactive, but this calm is misleading. Inside the magnetar, magnetic forces are constantly shifting and twisting. Imagine tectonic plates deep inside Earth, slowly moving and building pressure. In a magnetar, similar stresses build up, but instead of being driven by heat and motion, They are driven by magnetic energy. Eventually, the stress becomes too much for the crust to handle. When that happens, the crust cracks. This event is called a starquake. Unlike earthquakes on Earth, which release relatively small amounts of energy, a starquake releases an enormous burst of radiation. In a single moment, a magnetar can release more energy than the Sun produces in hundreds of thousands of years. These bursts can be detected across the galaxy, even though the magnetar itself is incredibly small. This ability to release such vast energy from such a small object is another reason magnetars stand apart from normal stars. A normal star releases energy slowly and steadily over billions of years. A magnetar releases energy suddenly and unpredictably. It is not a steady light source. It is more like a cosmic flash grenade, quiet until it explodes. To understand just how extreme magnetars are, consider what would happen if one came close to Earth. Even from a great distance, its magnetic field could wipe out electronics, erase data, and damage satellites. This would happen without any physical contact. The magnetar would not need to touch Earth or even be particularly close by cosmic standards. Its invisible magnetic influence alone would be enough to cause damage. This is why magnetars are sometimes described as more dangerous than black holes in certain ways. A black hole is deadly, but its danger zone is limited. You have to get very close to be affected. A magnetar's influence can reach far into space. It can affect objects across enormous distances through radiation and magnetism. And unlike black holes, magnetars do not announce themselves clearly. They can remain silent for long periods, then suddenly release a massive flare without warning. Scientists are deeply interested in magnetars not because they threaten us, but because they allow us to study physics at its limits. On Earth, we cannot recreate the conditions found inside or near a magnetar. No laboratory can produce such density or such magnetic strength. Magnetars act like natural experiments created by the universe itself. By observing them, scientists test theories about matter, gravity, and electromagnetism under conditions that cannot exist anywhere else. Another important point is that magnetars are rare. Not every massive star becomes a magnetar. Only a small fraction do, under very specific conditions. This rarity makes them even more fascinating. It also means that many magnetars may exist quietly, hidden from view, only revealing themselves when they release a sudden burst of energy. Each new magnetar discovered helps scientists refine their understanding of how stars die and how extreme objects form. At the most basic level, a magnetar teaches us a powerful lesson about the universe. Power does not always come from size. Some of the most powerful things in existence are small, dense, and invisible most of the time. A magnetar shows us that nature is capable of creating objects that feel almost impossible, objects that compress stars into city-sized spheres and turn magnetism into a force that can reshape reality. So when scientists describe magnetars as the most powerful objects known, they are not exaggerating for drama. They are describing a real class of objects that challenge our understanding and force us to rethink what is possible. A magnetar is not a star that shines. It is a star that has been pushed beyond its limits and transformed into something far stranger. It is a reminder that the universe is not just vast and beautiful, but also extreme, unpredictable, and endlessly fascinating. Long before a magnetar becomes one of the most powerful objects in the universe, it begins its life in a very familiar way, as a star. But not just any star. The story of a magnetar always starts with a giant, a star so massive that its fate is sealed from the moment it is born. These stars are many times heavier than our Sun. They burn brighter, hotter, and faster, and because of that, they live much shorter lives. A massive star is born inside a cloud of gas and dust. Gravity pulls this material together, until the core becomes hot enough to ignite nuclear fusion. Once fusion begins, the star shines brilliantly. For millions of years, it lives a balanced life. Gravity tries to crush it inward, while the energy from fusion pushes outward. This balance keeps the star stable, but unlike smaller stars, massive stars burn through their fuel at an incredible speed. They are powerful, but wasteful. They consume hydrogen quickly, then move on to heavier fuels like helium, carbon, and oxygen. As the star ages, its core becomes layered like an onion. Each layer burns a different type of fuel, producing heavier and heavier elements. This process continues until iron begins to form in the core. And this is where the story changes forever. Iron is a dead end for stars. Fusing iron does not release energy. Instead, it consumes energy. Once the core fills with iron, the star loses its ability to fight gravity. In a matter of seconds, the balance that held the star together for millions of years collapses. Gravity takes over completely. The core begins to fall inward at an unbelievable speed. Atoms are crushed together. Temperatures soar. The collapse becomes unstoppable. This sudden inward fall triggers one of the most violent events in the universe, a supernova. A supernova is not just an explosion, it is the violent death cry of a massive star. When the core collapses, it rebounds like a compressed spring. Shock waves race outward, tearing the star apart. The outer layers are blasted into space, creating a brilliant flash that can briefly outshine an entire galaxy. For a short time, this dying star becomes one of the brightest objects in the universe. But while the explosion is spectacular, the most important transformation happens at the center. The core, crushed by gravity, undergoes a radical change. Electrons are forced into protons, forming neutrons. Atomic structures collapse. Matter is no longer made of atoms as we know them. The core becomes a single, compact object made almost entirely of neutrons. This object is called a neutron star. A neutron star is already extreme. It is incredibly small, only about the size of a city, yet it contains more mass than the Sun. Its gravity is so strong that standing on its surface would flatten anything instantly. Time itself slows near it. Even light has a hard time escaping its pull. For most massive stars that do not become black holes, this neutron star is the final result. But sometimes something even stranger happens. In very rare cases, the newborn neutron star is born spinning extremely fast and carrying an enormous amount of magnetic energy. This happens because of the way the original star collapses. As the core shrinks, its rotation speeds up, much like a spinning ice skater pulling in their arms. At the same time, the star's original magnetic field becomes compressed into a much smaller space. This compression dramatically amplifies the magnetic field. In most neutron stars, this magnetic field is already incredibly strong. But in a tiny fraction of cases, the conditions are just right for the magnetic field to grow to absurd levels. When this happens, the neutron star becomes a magnetar. So why do only some neutron stars become magnetars? The answer lies in rarity and precision. Several conditions must line up perfectly. First, the original star must be massive enough, but not too massive. If it is too heavy, the collapse creates a black hole instead. If it is too light, the resulting neutron star will not have enough energy to become a magnetar. Second, the collapse must happen in a way that preserves extreme rotation. The newborn neutron star needs to spin very fast, often completing a rotation in just milliseconds. This rapid spin plays a key role in strengthening the magnetic field during the star's earliest moments. Third, the magnetic field itself must be amplified through processes that are still being studied. Scientists believe that turbulent motion inside the newborn neutron star can act like a powerful dynamo, supercharging the magnetic field to unimaginable levels. This process happens extremely quickly, within seconds after the supernova. If all these conditions are met, the neutron star is born as a magnetar. But if even one condition fails, the result is a normal neutron star instead. This is why magnetars are so rare. Out of the countless stars that have lived and died in the universe, only a small number ever become magnetars. Once formed, a magnetar's extreme magnetism defines its entire life. From the moment it is born, its magnetic field begins to twist and decay. This decay releases energy, which powers the magnetar's violent behavior. Unlike normal neutron stars that shine steadily, magnetars shine in bursts. They crack, flare, and erupt as their magnetic fields rearrange themselves. The birth of a magnetar is also a moment of chaos. The supernova that creates it often leaves behind a glowing cloud of debris expanding into space. At the center of this expanding shell sits the newborn magnetar, spinning rapidly, magnetism raging beneath its surface. Over time, the surrounding debris fades, but the magnetar remains, quietly spinning, waiting for its next outburst. It is important to understand that magnetars are not permanent monsters. Their power does not last forever. Over thousands to millions of years, their magnetic fields slowly weaken. As this happens, their violent activity decreases. Eventually, a magnetar may become quiet and difficult to distinguish from other neutron stars. In this sense, magnetars have a life cycle of their own, beginning in extreme violence and slowly fading into silence. Still, during their active years, magnetars represent the universe at its most extreme. Their birth alone requires a perfect storm of mass rotation and magnetic energy. This is why scientists study them so closely. Each magnetar carries information about the death of a massive star, the physics of collapse, and the limits of magnetism. The story of a magnetar's birth is a reminder that the universe does not create its most powerful objects easily. It takes millions of years of stellar life, followed by a moment of catastrophic collapse, to produce something so rare. A magnetar is not just born, it is forged through destruction. From a shining giant star to a collapsing core, from a supernova explosion to a city-sized object with the strongest magnetic field known. The journey from star to magnetar is one of the most dramatic transformations in nature. It is the story of how the universe turns death into power, and how the quiet darkness of space can hide monsters born in fire. Neutron stars and magnetars begin their lives in exactly the same way, and that shared origin often hides just how different they truly are. Both are born from the death of massive stars. Both are formed when a star collapses under its own gravity and explodes as a supernova. Both are crushed into objects only about the size of a city, yet heavier than the sun. From the outside, it would be easy to assume that neutron stars and magnetars are simply variations of the same thing, but once they're born, their behavior quickly separates them into two very different cosmic personalities. One is extreme but controlled. The other is unstable, violent, and unpredictable. A typical neutron star is already an object of extremes. It spins rapidly, has enormous gravity, and possesses a strong magnetic field. Many neutron stars appear to us as pulsars, sending out regular beams of radiation like cosmic lighthouses. These pulses are precise and steady. Some neutron stars rotate hundreds of times per second, yet they behave in a calm, predictable way. Their energy output is steady, their signals are reliable. In many ways, neutron stars are disciplined survivors of stellar death. Magnetars, on the other hand, are neutron stars that never learn to be calm. The biggest and most important difference between a normal neutron star and a magnetar is magnetic field strength. This one factor changes everything. A typical neutron star already has a magnetic field billions to trillions of times stronger than Earth's. That alone is hard to imagine, but a magnetar takes this to a completely different level. Its magnetic field can be hundreds or even thousands of times stronger than that of a normal neutron star. When scientists say magnetars have the strongest magnetic fields in the universe, they are not speaking loosely. No other known object comes close. This difference in magnetic strength is not a small upgrade, it is a complete transformation. Magnetism is not just a feature of magnetars, it is their driving force. In a normal neutron star, magnetism shapes how it emits radiation. In a magnetar, magnetism controls the star's structure, behavior, and fate. The magnetic field is so strong that it stores enormous amounts of energy inside the star. That energy is unstable, and instability leads to violence. Rotation is another key difference, but not in the way most people expect. Many neutron stars spin extremely fast, sometimes hundreds of times per second. Magnetars, surprisingly, often rotate more slowly. Some take several seconds to complete a single rotation. This seems backwards at first. If magnetars are more powerful, shouldn't they spin faster? The answer is no, because magnetars lose energy differently. In normal neutron stars, rotation is a major energy source. Their spinning motion powers their radiation beams. Over time, they gradually slow down, but they can remain stable for millions or even billions of years. Magnetars, however, lose energy rapidly through magnetic activity. Their intense magnetic fields act like powerful brakes, draining rotational energy and converting it into heat, radiation, and violent outbursts. As a result, magnetars slow down much faster than normal neutron stars. Energy output is where the difference becomes dramatic. A normal neutron star releases energy in a controlled, predictable way. Its radiation pulses are regular and measured. Scientists can track them with incredible precision. Magnetars do not follow this pattern. They are quiet for long periods, then suddenly release massive bursts of energy without warning. These bursts can take many forms, from short flashes of X-rays to enormous gamma-ray flares that briefly become some of the brightest events in the universe. This is why magnetars are far more violent than ordinary neutron stars. Their magnetic fields twist and strain the star's crust constantly. Imagine a solid shell being pulled and warped from the inside by invisible hands. Over time, the stress builds. Eventually, the crust cracks. These cracks release magnetic energy explosively, creating what scientists call starquakes. The resulting bursts of radiation can be detected across the galaxy. In seconds, a magnetar can release more energy than the Sun produces in hundreds of thousands of years. A normal neutron star almost never does this. Its magnetic field is strong, but stable. Its crust is under stress, but not enough to shatter violently. It may glitch slightly, speeding up or slowing down a bit, but it does not erupt with the same ferocity. This difference in stability is crucial. Neutron stars are extreme, but magnetars live on the edge of chaos. Another difference lies in how each object interacts with its surroundings. Normal neutron stars mainly affect nearby space through gravity and radiation. Magnetars affect space through magnetism itself. Their magnetic fields extend far beyond the star, influencing particles and radiation at great distances. This can create glowing clouds of charged particles and intense radiation environments that are hostile to anything nearby. In this sense, magnetars are not just objects. They are regions of distorted space filled with invisible force. To understand this difference more clearly, it helps to use a simple analogy. Imagine two spinning tops. Both are made from the same material. Both are spun into motion in the same way. The first top spins smoothly and evenly on a flat surface. It wobbles a little, but it stays upright and predictable. This is a normal neutron star. The second top is wrapped tightly, with powerful elastic bands pulling in every direction. It spins, but the tension inside it causes sudden jerks, cracks, and violent snaps. That second top is a magnetar. Another helpful comparison is to think of engines. A normal neutron star is like a well-tuned engine running at high speed. It produces a steady output and can keep going for a very long time. A magnetar is like an engine running with extreme pressure inside. Most of the time, it idles quietly, but when something gives way, it releases energy explosively. It is not designed for longevity. It is designed for intensity. This difference also explains why magnetars are rarer than normal neutron stars. Not every collapsing star produces the perfect conditions needed to create such extreme magnetism. Only a small fraction of neutron stars are born with magnetic fields strong enough to make them magnetars. And even among those, magnetars do not stay active forever. Their intense magnetism slowly decays. As it does, their violent behavior fades. Eventually, a magnetar may become quiet and resemble a more ordinary neutron star. Still, during their active phase, magnetars dominate the cosmic stage. Their bursts are so powerful that they can momentarily affect space across vast distances. In some cases, magnetar flares have been strong enough to disturb Earth's upper atmosphere from tens of thousands of light years away. No normal neutron star has ever done that. In summary, neutron stars and magnetars share the same birth, but they lead very different lives. Neutron stars are extreme survivors that settle into stable, predictable behavior. Magnetars and neutron stars push beyond stability, driven by magnetic forces so strong that they crack their own surfaces and unleash cosmic violence. The difference between them is not just a matter of degree, it is a difference in nature. Understanding this contrast helps explain why magnetars inspire both awe and caution among scientists. They are not simply bigger or brighter neutron stars. They are neutron stars taken to the breaking point, where neutron stars show us how far physics can stretch. Magnetars show us what happens when it finally snaps. To understand why magnetars are considered the most powerful objects in the universe, we first need to understand magnetism itself in the simplest possible way. Magnetism is a force. It is invisible, but we see its effects every day. A small magnet sticks to a refrigerator door. A compass needle points north because it follows Earth's magnetic field. This force comes from the motion and alignment of tiny particles inside matter. In everyday life, magnetism feels gentle and useful. It helps power motors, store data, and guide navigation. But in space, magnetism can grow into something far more extreme. At its heart, magnetism is about influence. A magnetic field is an area where magnetic force can act. Earth has a magnetic field that surrounds our planet like a protective bubble. It shields us from harmful radiation coming from the sun and deep space. Without it, life on Earth would be very different, possibly impossible. But Earth's magnetic field, as important as it is to us, is actually very weak by cosmic standards. Now imagine turning that gentle force up, not a little, not 1,000 times, but trillions of times stronger. That is where magnetars live. A magnetar's magnetic field is the strongest magnetic field known to exist anywhere in the universe. There is nothing else like it. No planet, no star, no black hole comes close. Even the strongest magnetic fields humans have ever created in laboratories are laughably weak compared to a magnetar. If you tried to compare them, it would be like comparing a candle flame to the surface of the sun. Earth's magnetic field is strong enough to move a compass needle and protect our atmosphere. A magnetar's magnetic field is strong enough to tear atoms apart. To appreciate how extreme this is, consider the numbers in a more human way. Earth's magnetic field is just strong enough to gently guide charged particles. A magnetar's magnetic field is so intense that it changes the shape of atoms themselves. Under such conditions, electrons no longer behave the way they do normally. Atoms become stretched and distorted, squeezed into strange forms. The space around the magnetar becomes a place where normal rules no longer apply. This is what scientists mean when they say magnetars push physics to its limits. Near a magnetar, magnetism is not just a force, it becomes a dominant feature of reality. The strength of a magnetar's magnetic field is not just a large number, it has real dramatic consequences. The field is so powerful that it can stress the solid crust of the magnetar itself. Imagine the strongest metal you can think of, far stronger than steel or diamond. Now imagine that metal being twisted and pulled by invisible forces from the inside. Eventually, even that crust breaks. These breaks are called starquakes, and they release enormous bursts of energy into space. This tells us something important. The magnetic field of a magnetar is strong enough to crack a star. Now let's compare this to Earth in a more direct and unsettling way. What would happen if a magnetar came close to our planet? First, it is important to say that this is extremely unlikely. There are no known magnetars anywhere near Earth, but imagining the scenario helps us understand their power. If a magnetar came close to Earth, even without touching us, its magnetic field would begin to affect our world long before the magnetar itself arrived. At a distance where gravity might not yet be dangerous, magnetism would already be doing damage. Satellites in orbit would fail. Their electronics would be scrambled or destroyed. Communication systems would break down. Power grids on the ground could collapse. Data stored on hard drives and magnetic storage would be erased instantly, and this would happen quietly. There would be no explosion, no fire, just invisible force overwhelming human technology. If the magnetar came even closer, the effects would grow worse. Radiation released from its magnetic activity would flood space. The atmosphere could be damaged. Living cells would be exposed to deadly energy. At very close distances, the magnetic field could begin to affect matter itself, disrupting chemical bonds. Life as we know it would not survive. The most chilling part of this scenario is that the magnetar does not need to do anything special to cause this damage. It does not need to explode. It does not need to flare. Its normal magnetic field alone would be enough. This is why scientists sometimes say magnetars are more dangerous than black holes in certain situations. A black hole is deadly, but only if you get extremely close. Its danger is localized. A magnetar's influence reaches far into space. Its magnetic field can affect objects from enormous distances. This power is almost unimaginable because it does not fit into our everyday experience. We are used to thinking of power in terms of size, speed, or explosions. Magnetars challenge that idea. Their power is quiet, invisible, and constant. It exists whether or not the magnetar is active. Even when a magnetar appears calm, its magnetic field is still one of the most extreme environments in the universe. Another reason this power is hard to imagine is that magnetars compress enormous energy into a very small space. The magnetar itself is only about the size of a city, yet its magnetic influence can extend thousands of kilometers into space. This concentration of energy is what makes magnetars so special. They show us that power does not always come from being big. Sometimes it comes from being tightly packed and intensely focused. Scientists study magnetar magnetic fields, not just out of curiosity, but because they reveal how nature behaves under extreme conditions. Near a magnetar, space itself behaves differently. Light can split into different paths. Empty space can act like a strange medium. These effects are predicted by advanced physics theories, but magnetars are one of the few places in the universe where they might actually occur. In this sense, magnetars are not just cosmic threats or curiosities. They are natural laboratories. They allow scientists to test ideas about electromagnetism, quantum physics, and gravity in ways that no experiment on Earth ever could. Every observation of a magnetar's magnetic field helps refine our understanding of reality. When we say that magnetars have the strongest magnetic fields in the universe, we are not using dramatic language for effect. We are describing a real and measurable fact. Their magnetic fields dominate everything around them. They shape matter, energy, and space itself. They turn magnetism into a force of cosmic destruction and creation. And yet, magnetars are also reminders of how strange and creative the universe can be. From the death of a massive star, nature produces an object that turns a familiar force into something almost magical in its intensity. Magnetism, which helps us stick notes to refrigerators, becomes a power capable of cracking stars and affecting worlds across space. This is why the magnetic field of a magnetar is almost impossible to fully imagine. It exists far beyond human scale. It is a force that makes the universe feel less like a calm, predictable place and more like a vast arena of extremes. Magnetars show us that even invisible forces can shape destiny, and that the universe is capable of far more power than our minds are comfortable with. When magnetism becomes as strong as it is near a magnetar, matter stops behaving the way we expect. The everyday rules that govern solids, liquids, gases, and even atoms begin to fail. To understand why magnetars are so strange, we need to explore what extreme magnetism does to matter itself, step by step, without complicated equations or heavy science words. The goal is simple: to see how a familiar force turns reality into something alien. Let's start small at the level of atoms. Atoms are the basic building blocks of everything around us. Each atom has a tiny nucleus at its center, surrounded by electrons moving in specific patterns. Under normal conditions, these electrons form neat, stable shapes. This is why materials have predictable properties. Metal is hard, water flows, air spreads out. All of this depends on atoms behaving in familiar ways. Near a magnetar, this order collapses. A magnetar's magnetic field is so strong that it grabs electrons and forces them to move differently. Instead of forming round, balanced clouds around the nucleus, electrons are squeezed and stretched along magnetic field lines. Atoms become long and thin, almost like tiny needles. Their normal shapes are destroyed. When atoms change shape, everything built from them changes too. Materials no longer behave like materials. They behave like something entirely new. This is the first sign that normal physics is failing. When atoms stretch, matter itself stretches. Solids that would normally resist force begin to behave strangely. The crust of a magnetar, which is already harder than anything we know on Earth, is constantly under stress. Magnetic forces pull and twist it from the inside. Imagine the strongest steel ever created, being bent slowly by invisible hands. Over time, even that steel would crack. On a magnetar, this is exactly what happens. The crust cannot relax. It cannot flow gently like lava or bend like plastic. It resists until it suddenly breaks. These breaks release enormous amounts of energy. That energy escapes as powerful bursts of radiation. This is why magnetars experience starquakes. They are not caused by movement deep inside like earthquakes on Earth. They are caused by magnetic stress overwhelming matter itself. This brings us to magnetic pressure, one of the most important ideas when talking about magnetars. Pressure is usually something we associate with gases, liquids, or gravity. Air pressure pushes on our bodies. Water pressure increases as you go deeper into the ocean. Gravity creates pressure inside planets and stars. But near a magnetar, magnetism creates pressure too, and it can be stronger than any other kind. Magnetic pressure is the force exerted by a magnetic field on charged particles and matter. In normal conditions, magnetic pressure is weak. We barely notice it. Near a magnetar, magnetic pressure becomes overwhelming. It presses on matter from all directions, squeezing it, stretching it, and locking it into strange configurations. Matter cannot move freely. Particles are forced to follow magnetic field lines, whether they want to or not. In some regions near a magnetar, magnetic pressure can become stronger than gravity itself. This is a shocking idea because gravity is usually the strongest force on large scales. Stars, planets, and galaxies exist because gravity dominates. But locally, right near the surface of a magnetar, magnetism can win. It can control how particles move, how energy flows, and how matter is arranged. This does not mean gravity disappears. The magnetar's gravity is still immense, but magnetism adds a new layer of control, bending reality in ways gravity alone never could. The two forces compete and interact, creating conditions that do not exist anywhere else in the universe. One of the strangest consequences of this is how light behaves. Normally, light travels in straight lines unless gravity bends it. Near a magnetar, magnetism can also affect light. The space around the magnetar becomes so distorted that light can split into different paths. Empty space itself behaves like a strange material. This idea sounds impossible, but it is predicted by modern physics and supported by observations. When empty space stops acting empty, we know we are far from normal conditions. Another mind-blowing effect is how matter near a magnetar becomes locked into place. Charged particles like electrons and ions spiral tightly along magnetic field lines. They cannot move sideways easily. This makes the environment around a magnetar highly organized and highly constrained. Energy builds up instead of spreading out smoothly. When it finally escapes, it does so violently. This is why magnetar outbursts are so sudden and intense. Energy is trapped by magnetic fields until the pressure becomes too great. When the field rearranges itself, the trapped energy is released all at once. It is like stretching a rubber band to its absolute limit and then letting it snap. But instead of a rubber band, it is a star-sized magnetic structure snapping across space. Under these conditions, normal physics equations begin to break down. The formulas that describe how materials bend, how heat flows, and how particles move were developed for environments like Earth or the Sun. They are not built for magnetic fields that can reshape atoms and distort space. Scientists must use advanced theories that combine electromagnetism, quantum mechanics, and relativity just to begin describing what is happening. Even then, many questions remain unanswered. This is why magnetars are so important to science. They are not just powerful objects. They are places where our understanding of nature is tested to its limits. When magnetism becomes strong enough to overpower atomic structure, we are forced to rethink what matter really is. Is matter solid because of its atoms, or because of the forces holding those atoms together? Near a magnetar, those forces change, and matter becomes something unfamiliar. To make this easier to imagine, think of matter on Earth as a neatly stacked wall of bricks. Each brick represents an atom, held in place by mortar. Under normal conditions, the wall is stable. Gravity presses down, but the structure holds. Near a magnetar, magnetism is like a powerful force pulling the bricks sideways, while gravity presses down from above. The wall is twisted in directions it was never designed to handle. Eventually, cracks appear, and the wall collapses in violent bursts. This collapse is not destruction for its own sake, it is energy release. The magnetar's magnetic field stores energy like a tightly wound spring. Matter resists that pressure until it cannot anymore. When it fails, the stored energy escapes as radiation that can travel across the galaxy. All of this shows why normal physics fails near a magnetar. The assumptions we rely on stop being true. Atoms are no longer stable shapes. Matter is no longer free to move normally. Space itself no longer behaves as empty nothingness. Forces we think of as secondary suddenly become dominant. And yet, the universe allows this to happen naturally. Magnetars remind us that the laws of physics are not broken. They are simply being pushed into extreme territory. The same rules still apply, but their outcomes look strange and unfamiliar. This is what makes magnetars both terrifying and fascinating. They show us that reality is flexible, and that under the right conditions, the universe can reshape even its most basic ingredients. When we say magnetars are mind-blowing, This is what we mean. Not just that they are powerful, but that they reveal a version of matter that we never experience. A version where magnetism rules, atoms stretch, and the solid ground of physics turns uncertain. Magnetars are not just objects in space. They are windows into the extreme edge of reality itself. A starquake is one of the most violent events ever observed in the universe, and yet it begins in a surprisingly familiar way. Just like earthquakes on Earth, starquakes are caused by stress building up until something finally breaks. The difference is scale. On Earth, an earthquake releases energy stored in moving tectonic plates. On a magnetar, a starquake releases energy stored in the strongest magnetic field known to exist. When that release happens, the result is so powerful that it can shake space itself. To understand a starquake, we first need to understand the surface of a magnetar. Unlike normal stars, which are made of hot, flowing gas, a magnetar has a solid crust. This crust is not rock or metal as we know it. It is far denser and stronger than anything on Earth. It is often described as a rigid shell made of tightly packed atomic nuclei, locked into place by immense gravity. Under normal circumstances, nothing could break this crust. But magnetars are not normal circumstances. The crust of a magnetar is constantly under attack from within. Beneath it lies an ocean of ultra-dense matter and an enormous magnetic field. This magnetic field is not stable or calm. It twists, shifts, and rearranges over time. As it does, it pulls on the crust above it, stretching and stressing it from the inside. Imagine the Earth's crust being pulled apart, not by moving plates, but by invisible forces pushing and twisting it in every direction at once. This is why magnetars crack like Earth. The process is deeply similar in concept, even though the forces involved are vastly different. On Earth, tectonic plates slowly move, building stress along fault lines. For years or centuries, nothing happens. Then suddenly, the stress becomes too great and the ground snaps. Energy that has been stored for a long time is released in seconds. On a magnetar, magnetic forces play the role of tectonic plates. They shift slowly, almost silently, until the crust can no longer hold. When the crust finally breaks, a starquake occurs. But calling it a quake almost understates the violence. The energy released in a starquake is beyond anything we can truly imagine. In just a fraction of a second, a magnetar can release more energy than the sun produces in hundreds of thousands of years. This energy does not come out as shaking ground. It comes out as intense bursts of X-rays and gamma rays, the most energetic forms of light. These bursts race outward at the speed of light, spreading through space like a cosmic scream. What makes starquakes even more dramatic is how fast they happen. The buildup of stress may take years or decades, but the release is almost instantaneous. In seconds, or even milliseconds, enormous amounts of magnetic energy are converted into radiation. There is no gradual warning. One moment the magnetar appears calm, the next it erupts. This sudden release is why starquakes are so dangerous and so fascinating. They show how energy can be stored quietly and then unleashed all at once when a critical limit is crossed. Scientists have observed real starquakes, and their discoveries read like something out of science fiction. Some magnetar flares have been so powerful that they temporarily affected Earth, even though the magnetar was tens of thousands of light years away. Satellites detected sudden spikes in radiation. Earth's upper atmosphere responded. Instruments designed to study solar flares were overwhelmed by signals coming from deep space. In one famous event, a magnetar released a giant flare so intense that it briefly saturated detectors across the solar system. For a moment, it became one of the brightest sources of gamma rays ever recorded. And this came from an object smaller than a city, located on the far side of our galaxy. These observations confirmed something scientists had suspected for years. Starquakes are not minor disturbances. They are among the most energetic events the universe can produce without completely destroying the object that creates them. This leads to an important question. Why don't magnetars tear themselves apart when they release so much energy? The answer lies in balance. Even though the energy released is enormous, it is still only a fraction of the total energy stored in the magnetar's magnetic field. The star survives, damaged but intact. Its crust may crack and shift, but gravity holds everything together. Over time, the magnetic field continues to twist, setting the stage for future starquakes. This cycle of stress and release can repeat many times over a magnetar's life. Starquakes are often called the loudest events in the universe, not because they make sound in the way we understand it, but because of how powerful their signals are. In space, sound cannot travel through empty vacuum, but energy can. And starquakes send out some of the strongest energy signals ever detected. If space could carry sound, a starquake would be deafening beyond comprehension. The radiation from a starquake can briefly dominate the energy environment of an entire region of the galaxy. For a short time, everything else fades into the background. This is why astronomers around the world pay close attention when magnetars flare. These events provide rare opportunities to study extreme physics in action. Another reason starquakes are so important is that they help scientists understand the internal structure of magnetars. Just as earthquakes on Earth reveal information about our planet's interior, starquakes reveal information about what lies beneath a magnetar's crust. By studying how the radiation changes during a flare, scientists can learn about the strength of the crust, the behavior of the magnetic field, and the nature of ultra-dense matter. In this way, starquakes turn destruction into knowledge. It is also worth noting that not all starquakes are equal. Some are relatively small, producing brief flashes of X-rays. Others are massive, producing giant flares that can be detected across galaxies. What determines the size of a starquake is how much stress has built up and how the magnetic field rearranges itself during the break. This unpredictability adds to the magnetar's reputation as a cosmic wildcard. From a human perspective, starquakes are terrifying events. They remind us how fragile our technology is compared to cosmic forces. A single magnetar flare, if close enough, could disrupt satellites, communications, and power systems on Earth. And yet, from a scientific perspective, they are incredible gifts. Each one offers a glimpse into conditions that cannot be recreated anywhere else. Starquakes show us that even the hardest objects in the universe can break. They show us that magnetism, when pushed to extremes, can overpower matter itself. And they show us that the universe does not release its greatest energies gradually. Sometimes it waits, builds pressure silently, and then releases everything in a single, overwhelming moment. This is why starquakes hold such a dramatic place in the story of magnetars. They are the moments when the monster reveals itself, when the quiet, spinning star suddenly cracks and screams across space. They are reminders that beneath the calm surface of the universe, unimaginable forces are always at work, waiting for the moment when something finally gives. A giant flare from a magnetar is one of the most dramatic sights the universe can offer, even though no human eye will ever see it directly. If we could watch one from a safe distance, it would not look like a slow-burning star or a spreading cloud of fire. It would appear as a sudden, blinding flash of energy erupting from a tiny point in space, brighter for a brief moment than almost anything else in the galaxy. There would be no warning glow, no gradual build-up. One instant, the magnetar would seem quiet and ordinary. The next, it would unleash a pulse of energy so intense that it would briefly dominate the high-energy sky. A magnetar flare begins deep inside the star, where magnetic forces have been twisting and tightening for years. When the magnetic field finally snaps into a new configuration, energy that has been trapped and compressed is released almost instantly. This release blasts outward along the magnetic field lines, producing a violent storm of radiation. The first fraction of a second is the most extreme. Scientists call this the initial spike. During this moment, The magnetar releases an enormous amount of energy in gamma rays, the most energetic form of light known. If instruments are pointed in the right direction, the signal is unmistakable. It is sharp, sudden, and overwhelming. Visually, if we could translate gamma rays into visible light, a giant flare would look like a blinding flash followed by a fading glow. The flash itself lasts less than a second, but it carries more energy than almost any other event in the universe. After that, a softer tail of radiation follows, lasting for minutes. This tail pulses as the magnetar continues to rotate, sending out waves of energy, like a wounded animal, still roaring after the initial strike. The entire event is short by cosmic standards, but its impact is enormous. The amount of energy released in a giant flare is difficult to comprehend, because it exists far outside human experience. In less than 1 second, a magnetar can release as much energy as the sun produces in hundreds of thousands of years. The sun shines steadily, day after day, year after year, powered by nuclear fusion. A magnetar flare releases its energy in a sudden burst powered by magnetic collapse. This difference in timescale is what makes magnetar flares so terrifying. They compress vast amounts of energy into moments. To make this more relatable, scientists often compare magnetar flares to nuclear explosions. A single nuclear bomb releases a tremendous amount of energy, enough to devastate a city. Now imagine not one bomb, but billions upon billions of them detonating at the same time. Even that comparison falls short. The energy in a giant magnetar flare far exceeds the combined output of all nuclear weapons ever built by humanity. And it does so without producing fire, smoke, or shockwaves in the usual sense. The destruction is carried by radiation itself. Despite this staggering power, Earth can detect magnetar flares from incredibly far away. This is one of the most astonishing aspects of these events. Magnetars that are tens of thousands of light years away can still be felt here. Satellites orbiting Earth, designed to monitor solar activity or distant cosmic explosions, suddenly register spikes in gamma rays. Instruments may briefly overload. For a moment, the detectors cannot tell where the energy is coming from, only that something extraordinarily powerful has happened. In some recorded cases, magnetar flares were so intense that they affected Earth's upper atmosphere. Ionization levels changed, radio signals were disturbed, and all of this happened because of an event that took place on the other side of the galaxy. No other type of star routinely produces effects at such distances without destroying itself in the process. This raises an obvious and unsettling question. If magnetar flares are so powerful, why don't they destroy everything around them? Why don't they tear galaxies apart or rip stars to pieces? The answer lies in direction, duration, and scale. A giant magnetar flare releases a huge amount of energy, but it does so very briefly and mostly in narrow beams aligned with its magnetic field. The energy spreads out rapidly as it travels through space. By the time it reaches distant regions, it is still detectable, but no longer destructive. The universe is vast, and even the most violent events lose intensity as they expand into that vastness. Another important point is that magnetar flares release energy, not mass. They do not throw large amounts of matter outward like supernova. A supernova physically tears a star apart and floods space with debris. A magnetar flare is more like a powerful flashbulb going off in space. It is blinding, intense, and energetic, but it does not carry enough material to cause large-scale destruction across a galaxy. This is why magnetar flares are sometimes described as cosmic explosions without destruction. They are violent but contained. They release energy, but leave the overall structure of the galaxy intact. Even the magnetar itself survives, scarred but still spinning. Its crust may crack, its magnetic field may rearrange, but gravity keeps the star together. Over time, it may flare again, repeating the cycle. The emotional impact of these events comes from this contrast. Something so small produces something so powerful, yet the universe absorbs it almost calmly. Galaxies continue to rotate, stars continue to shine. Life, if it exists nearby, may never even notice. This reminds us that the universe operates on scales that dwarf human concerns. What feels apocalyptic to us is often just a brief flicker in cosmic time. At the same time, magnetar flares are a reminder of vulnerability. Our planet is safe largely because of distance and luck. If a magnetar were close enough and aimed just right, a giant flare could cause serious harm to Earth's technology. Satellites could fail, power grids could be disrupted, communications could be damaged. Life itself might survive, but our modern systems would struggle. The fact that this has not happened is not because magnetars are gentle, but because space is vast. Scientists study giant flares with a mix of awe and caution. Each detected flare provides valuable data about extreme magnetism, radiation, and the behavior of matter under stress. At the same time, each flare is a reminder that the universe contains forces far beyond anything we can control or predict completely. Magnetars do not follow schedules. They erupt when internal stresses demand it. Perhaps the most remarkable thing about giant flares is that they allow us to observe the universe at its limits without total destruction. They are windows into extreme physics that do not require the death of a star or the collapse of a galaxy. They show us that nature can release incredible power in controlled bursts, governed by invisible magnetic structures rather than explosions of matter. In the end, giant magnetar flares are both terrifying and beautiful. They are terrifying because of their raw power and unpredictability. They are beautiful because they reveal the elegance of physical laws operating under extreme conditions. A magnetar flare is not chaos for its own sake. It is the universe adjusting itself, releasing tension, and moving on. These cosmic explosions remind us that the universe does not need to destroy itself to show its strength. Sometimes it only needs a moment, a single flash, a brief scream of energy crossing the darkness, and then once again, silence. Gamma-ray bursts are among the most mysterious and powerful signals ever detected from space. And for decades, they puzzled scientists more than almost any other cosmic phenomenon. These bursts appear suddenly without warning as intense flashes of gamma rays, the most energetic form of light in the universe. They can last anywhere from a tiny fraction of a second to several minutes. And during that brief time, they can outshine entire galaxies. What makes gamma ray bursts so strange is not just their power, but their unpredictability. They come from random directions in the sky. They vanish almost as quickly as they appear, and for much of human history, we had no idea what was causing them. Gamma rays themselves are not something we can see with our eyes. They are invisible, dangerous, and extremely energetic. On Earth, gamma rays are blocked by our atmosphere, which is a good thing because direct exposure would be deadly. To detect gamma ray bursts, scientists rely on satellites in space, constantly watching the sky for sudden spikes of high-energy radiation. When one appears, alarms go off in observatories around the world. Telescopes quickly turn toward the source, trying to catch whatever remains after the initial flash fades. Over time, scientists discovered that gamma ray bursts come in two main types: long bursts and short bursts. This simple division turned out to be one of the most important clues in understanding their origins. Long gamma ray bursts last more than 2 seconds, and sometimes much longer. These bursts are usually linked to the deaths of extremely massive stars. When such a star collapses and explodes as a powerful supernova, it can produce jets of energy that punch through the star and blast into space. If one of those jets is pointed toward Earth, we see it as a long gamma ray burst. These events are catastrophic. The star is destroyed. A black hole or neutron star is left behind. The explosion reshapes the surrounding region of space. Long gamma ray bursts are among the most violent deaths in the universe. Short gamma ray bursts are different. They last less than 2 seconds, sometimes only a few milliseconds. They are harder to study because they vanish so quickly. For a long time, scientists did not know what caused them. Eventually, strong evidence showed that many short gamma-ray bursts come from the collision of two neutron stars, or a neutron star merging with a black hole. These collisions release enormous energy in a brief moment, producing a short, sharp burst of gamma rays. But here is where the mystery deepens. Not all short gamma-ray bursts fit neatly into this explanation. Some appear to come from regions of space where no recent collisions should be happening. Some are followed by strange afterglows that do not match merger models. And some look suspiciously similar to something else scientists already know very well: magnetar flares. This is where magnetars enter the story. Magnetars are capable of producing giant flares that release enormous amounts of gamma radiation in a very short time. From a great distance, a powerful magnetar flare can look almost identical to a short gamma-ray burst. In fact, if such a flare occurred in a nearby galaxy, it could easily be mistaken for a classic short gamma-ray burst caused by a neutron star collision. This realization changed the way scientists think about gamma-ray bursts. One of the strongest pieces of evidence linking magnetars to gamma-ray bursts came when scientists observed a giant flare from a magnetar inside our own galaxy. The signal was so powerful that if it had come from farther away, it would have been classified as a short gamma-ray burst. This showed that magnetars are not just capable of producing gamma rays, but of producing them in exactly the way some mysterious bursts appear. So how could a magnetar create something that looks like a gamma-ray burst? The answer lies in magnetic collapse and sudden energy release. Inside a magnetar, enormous magnetic stress builds up over time. When that stress is released during a starquake or magnetic reconnection event, energy is unleashed almost instantly. This energy travels outward along magnetic field lines and escapes as intense gamma radiation. The entire process can happen in milliseconds. From far away, all an observer sees is a sudden flash of gamma rays, and then nothing. That is exactly how a short gamma-ray burst looks. However, magnetar-related bursts are not as destructive as those caused by massive stellar explosions or neutron star mergers. The magnetar survives. The galaxy survives. Space absorbs the energy and moves on. This makes magnetar bursts a kind of cosmic illusion. They look like catastrophic endings, but they are actually violent outbursts from objects that continue to exist afterward. Scientists are still working to understand how many gamma-ray bursts are caused by magnetars and how many come from other sources. This is not an easy problem to solve. Gamma-ray bursts happen far away and their signals are brief. Often, by the time telescopes point toward the source, the event is already over. Scientists must rely on indirect clues such as how long the burst lasted, how energetic it was, and what kind of afterglow followed. In some cases, magnetar bursts leave behind lingering X-ray signals that fade over time. In others, they appear completely isolated. Sorting these events into categories is like trying to identify animals based on a single footprint in the dark. The data is limited, and interpretations can change as new observations arrive. There is also debate about whether newly formed magnetars, created during supernova explosions or neutron star mergers, could produce gamma-ray bursts during their first moments of life. Some theories suggest that a rapidly spinning newborn magnetar could power a burst by converting rotational energy and magnetic energy into gamma rays. Others argue that black holes are more efficient at doing this. The truth may be that the universe uses multiple methods to create similar-looking events. This uncertainty is exactly what makes the magnetar gamma-ray burst connection so exciting. It shows us that the universe does not always follow simple rules. Different processes can produce similar results. A distant observer may see the same flash of gamma rays, but the cause could be a collapsing star, a cosmic collision, or a cracking magnetar. Why does this connection matter so much? It matters because gamma-ray bursts are used as tools to study the universe. They are bright enough to be seen across billions of light years, making them valuable markers of distant cosmic events. If scientists misunderstand what causes them, they may misinterpret what they're seeing. Knowing which bursts come from magnetars helps refine our understanding of how often stars collide, how often massive stars die, and how energy is released in the universe. It also matters because magnetars offer a way to study extreme physics without total destruction. A magnetar flare is like a controlled experiment compared to a supernova. The object survives, allowing repeated observations over time. This gives scientists more chances to test theories about magnetism, radiation, and matter under extreme stress. Finally, this connection matters because it reminds us that the universe is efficient and creative. It reuses mechanisms. Magnetic energy, gravity, and rotation can combine in different ways to produce similar cosmic signals. What looks like a single phenomenon from afar may actually be many different stories layered together. Magnetars and gamma-ray bursts sit at the edge of what we understand. They blur the lines between categories, they challenge our assumptions, and they force scientists to stay humble. Every new burst detected is a reminder that the universe still holds surprises, and that even the most powerful flashes of light may come not from destruction, but from a star cracking under the pressure of its own invisible strength. In connecting magnetars to gamma-ray bursts, we are not closing a mystery, we are opening a deeper one, and in that mystery lies some of the most exciting science of our time. Finding a magnetar is not like spotting a bright star in the night sky. In fact, magnetars are some of the hardest objects in the universe to detect. They do not shine steadily. They do not announce their presence clearly. Most of the time, they're quiet, faint, and hidden among countless other cosmic objects. Scientists often compare the search for magnetars to listening for a single crack of thunder during a silent night, without knowing when or where it will happen. The main reason magnetars are hard to find is their silence. Unlike normal stars, they do not glow in visible light. Unlike pulsars, many do not send out steady radio signals. A magnetar can sit unnoticed for years, doing nothing dramatic at all. If it does not flare or burst, there is almost no obvious sign that it exists. This means scientists cannot simply scan the sky and count magnetars easily. They usually discover them only when something violent happens. This is where space telescopes come in. Space telescopes are not like backyard telescopes that look at stars and planets in visible light. Many of the most important telescopes for studying magnetars are designed to see forms of light that never reach the ground. Earth's atmosphere blocks X-rays and gamma rays, which is good for life, but bad for astronomy. To study magnetars, scientists must place telescopes above the atmosphere, floating in space, constantly watching the sky for sudden flashes of high-energy radiation. These telescopes do not take pictures in the usual sense. Instead, they act like extremely sensitive counters. They measure how many high-energy photons arrive, how strong they are, and how quickly they come and go. When a magnetar releases a burst of X-rays or gamma rays, these detectors light up with data. Computers analyze the signal instantly, looking for patterns that match known magnetar behavior. X-rays and gamma rays are the key to detecting magnetars because that is where most of their energy is released. A quiet magnetar may still emit faint X-rays, glowing softly in high-energy light even when it appears invisible in other wavelengths. During bursts and flares, this glow becomes a sudden blaze. Satellites designed to detect gamma-ray bursts are often the first to notice magnetar activity, even if that was not their original purpose. When a sudden spike in gamma rays is detected, scientists around the world receive alerts within seconds. Other telescopes quickly turn toward the source. X-ray observatories look for lingering emission, Optical telescopes search for faint afterglows. Radio telescopes listen for unusual signals. This rapid, coordinated response is crucial because magnetar events fade quickly. Miss the moment, and the evidence may disappear. Another powerful tool scientists use to identify magnetars is timing. Magnetars spin, and that spin leaves a signature. As a magnetar rotates, it can send out pulses of radiation at regular intervals, similar to a lighthouse beam. These pulses are not always visible in radio waves, but they often appear in X-rays. By measuring the timing of these pulses, scientists can calculate how fast the magnetar is spinning. Spin tracking reveals something very important. Magnetars slow down over time much faster than normal neutron stars. This rapid slowing is a clue that their magnetic fields are extremely strong. By measuring how quickly the spin period changes, scientists can estimate the strength of the magnetic field, even though they cannot measure it directly. This indirect method is one of the most important ways magnetars are identified. Timing also helps scientists understand magnetar behavior. Sudden changes in spin rate, called glitches, often occur around the same time as starquakes or bursts. These glitches act like fingerprints, linking rotational behavior to violent magnetic events. By studying them, scientists learn how the magnetar's interior and magnetic field interact. Some of the most famous magnetar discoveries came as complete surprises. In several cases, telescopes detected powerful gamma-ray flashes that were initially thought to be distant cosmic explosions. Only later did scientists realize the source was a magnetar inside our own galaxy. These moments forced astronomers to rethink what magnetars were capable of and how often they might be mistaken for other phenomena. One major surprise was discovering that magnetars can go quiet for long periods and then suddenly wake up. Some magnetars were only discovered after they erupted unexpectedly. Others were first seen as faint X-ray sources and only later revealed their true nature through bursts and flares. This unpredictable behavior makes magnetars exciting but frustrating targets. Another surprise was finding that magnetars are not all the same. Some are extremely active, releasing frequent bursts. Others are calm, flaring only once in a long while. Some rotate relatively slowly, while others spin faster than expected. Each new magnetar discovered adds another piece to the puzzle and often raises new questions. Scientists also use the environment around magnetars to help identify them. Many magnetars are found near the remains of supernova explosions. These expanding clouds of debris act like cosmic signposts, marking where a massive star once died. If a strange X-ray source is found near such a remnant, scientists suspect a neutron star, and possibly a magnetar, lies at its center. Despite all these tools, detecting magnetars remains challenging. There may be many more magnetars in our galaxy than we currently know about. Some may be too quiet to detect with current instruments. Others may be hidden behind thick clouds of gas and dust that block even X-rays. Future telescopes with greater sensitivity will likely reveal many more. The process of detecting magnetars shows how modern astronomy works behind the scenes. It is not about a single telescope or a single observation. It is about networks of instruments, constant monitoring, rapid communication, and careful analysis. It is about patience and surprise. Years of silence can be followed by a single second that changes everything. Perhaps the most fascinating part of magnetar detection is that we often find them by accident. Telescopes searching for something else suddenly catch a signal they cannot ignore. A brief flash, an unexpected pulse, a spike of energy that does not fit any known pattern. Those moments are when new magnetars are born in our catalogues. In this way, magnetars remind us that the universe is not fully mapped or understood. Even with advanced technology, we are still discovering powerful objects hiding in plain sight. Each magnetar found is proof that space still holds secrets, waiting for the right moment to reveal themselves. Detecting magnetars is not just about finding rare objects. It is about learning how to listen to the universe. Magnetars speak in bursts, pulses, and silence. Scientists have learned to hear those signals, even when they're faint, brief, or confusing. And as our tools improve, we will hear more of them, uncovering new monsters quietly spinning in the dark. The question of whether a magnetar could destroy Earth is one of the most common and emotionally charged questions scientists hear, and it makes sense why. When you learn that an object the size of a city can release more energy in seconds than the sun does in hundreds of thousands of years, fear feels natural. But the real answer is far more interesting than a simple yes or no, and it requires separating what magnetars can do from what they are likely to do. The truth lies in distance, direction, and probability, not in raw power alone. First, let's talk about distance, because distance is everything in space. Magnetars are incredibly powerful, but that power fades quickly as it spreads out across the vastness of the universe. Right now, the nearest known magnetars are tens of thousands of light years away. That distance is so enormous that even their most violent flares reach Earth as little more than faint whispers detected by sensitive instruments. To pose a serious threat to our planet, a magnetar would need to be extremely close in cosmic terms, far closer than any known magnetar is today. Scientists estimate that for a magnetar to cause major damage to Earth, it would need to be within a few thousand light years, and even closer to cause truly severe effects. To put that in perspective, our galaxy is about 100,000 light years across. The dangerous zone is a tiny bubble within that vast space. The odds of a magnetar forming inside that bubble and aiming its energy toward Earth are extremely low. Now let's imagine a hypothetical scenario, purely for understanding, where a magnetar did exist close enough to matter. What would actually happen? The first thing to understand is that a magnetar would not rip Earth apart or pull it apart with gravity. Magnetars are not massive enough to destroy planets through gravitational forces unless you are unimaginably close, far closer than any realistic scenario allows. The danger comes not from gravity, but from radiation and magnetism. If a nearby magnetar released a giant flare, and Earth happened to be in the path of that flare, the first systems affected would be our technology. Satellites orbiting Earth would be exposed to intense radiation. Their electronics could be damaged or permanently destroyed. GPS systems could fail. Communication satellites could go offline. Weather satellites could stop functioning. All of this could happen very quickly, in minutes or even seconds. On the ground, the effects would depend on the strength of the flare and how Earth's magnetic field interacts with it. Strong radiation could disrupt radio communication and damage power grids, similar to what strong solar storms can do, but on a larger scale. Transformers could overload. Blackouts could spread across regions. Data stored in magnetic systems could be corrupted or erased. Modern civilization, which depends heavily on electronics, would feel the impact almost immediately. The atmosphere would also play a critical role. Earth's atmosphere is an excellent shield. It absorbs and scatters much of the harmful radiation coming from space. In a severe magnetar flare scenario, the upper atmosphere could become heavily ionized. This would disrupt radio signals and possibly damage parts of the ozone layer. However, destroying the atmosphere entirely is extremely unlikely. Even powerful cosmic events struggle to strip a planet of its atmosphere unless they occur repeatedly or at extremely close range. What about life itself? This is where fear often takes over, but science provides a calmer picture. Surface life on Earth would likely survive a distant magnetar flare. Radiation levels could increase temporarily, especially at high altitudes and near the poles, but they would not instantly sterilize the planet. Life on Earth has survived far worse events in the past, including massive asteroid impacts and intense solar activity. Deep ocean life underground life, and even most surface ecosystems would remain protected by water, soil, and the atmosphere. That said, a close and powerful magnetar flare could be extremely disruptive to human society. It could damage infrastructure on a global scale. Recovery could take years. The danger is not extinction, but vulnerability. Our technology makes us powerful, but also fragile. So why are we safe right now? The simplest answer is that space is enormous, and magnetars are rare. The odds of one forming close enough to Earth to pose a real threat are extremely low. Even if one did form nearby, it would also need to aim its most powerful flare directly at Earth. Magnetar flares are not evenly distributed in all directions. They are shaped by magnetic field lines and often focused into specific regions of space. Earth would need to be in exactly the wrong place at exactly the wrong time. There is also time to consider. Magnetars do not appear suddenly next door without warning. They form from massive stars which live millions of years before collapsing. Astronomers monitor nearby massive stars closely. If one were likely to produce a magnetar near Earth, we would know about it long before it became dangerous. The universe does not hide these threats quietly at close range. This brings us to the most important parts of this discussion: separating science from fear. Popular media often presents cosmic threats as sudden, unstoppable disasters. In reality, astronomy is a science of probability, distance, and gradual change. Magnetars are powerful, but power alone does not equal danger. Context matters. Fear tends to focus on what is possible, while science focuses on what is likely. Yes, a magnetar flare could damage Earth under very specific conditions, but those conditions are so rare that they fall far below many risks we already accept, such as asteroid impacts, supervolcanoes, or even extreme solar storms. And unlike many Earth-based threats, magnetars are far away, observable, and governed by predictable physics. There is also a psychological aspect to magnetars that makes them especially frightening. They are invisible. They act suddenly. They release energy beyond human scale. These traits trigger deep fears, but the same universe that creates magnetars also creates distance, randomness, and balance. The same laws of physics that allow magnetars to exist also ensure that they are unlikely to threaten us directly. In fact, magnetars teach us something reassuring as well as humbling. They show us that the universe is not actively hostile. It is extreme, but not malicious. It produces incredible forces, but those forces are usually isolated and self-contained. Even the most violent magnetar flares do not tear galaxies apart. They flare, release tension, and fade back into silence. Understanding magnetars replaces fear with perspective. Instead of imagining instant destruction, we see a complex system governed by rules. We see that Earth is protected not just by luck, but by distance, atmosphere, and magnetic shielding. We see that the universe gives us time to observe, understand, and prepare. So could a magnetar destroy Earth? In theory, under very specific and extremely unlikely conditions, it could cause serious harm to our technology and environment. In reality, the chances are so small that they should inspire curiosity, not fear. Magnetars are not ticking time bombs aimed at us. They are distant reminders of how powerful nature can be, and how fortunate we are to live in a quiet corner of a very energetic universe. The real value of asking this question is not in worrying about destruction, but in appreciating understanding. When we replace fear with knowledge, magnetars stop being cosmic monsters and become something far more meaningful. Lessons in scale, power, and perspective. Magnetars exist at a point where our understanding of physics begins to stretch, bend, and in some cases, quietly fail. They are not just powerful objects in space. They are places where the laws we rely on every day are pushed into conditions so extreme that even our best theories start to show cracks. This is why magnetars matter so deeply to scientists. They are not curiosities. They are stress tests for reality itself. Most of modern physics is built on theories that work incredibly well in ordinary conditions. They explain how planets move, how light travels, how electricity flows, and how atoms behave. These theories are tested constantly on Earth and across the solar system, and they almost always give the right answers. But magnetars are not ordinary. They combine extremes in a way that few other objects do. Enormous gravity, unimaginable magnetism, crushing density, violent energy release. When all of these come together, the usual rules stop being enough. One of the first places current theories begin to struggle is in describing matter itself. On Earth, matter is made of atoms, with predictable shapes and behaviors. Even inside ordinary stars, matter behaves in ways scientists can model well. Inside a magnetar, atoms are no longer stable structures. Electrons are forced into unnatural motion. Atomic shapes stretch and collapse. The physics that describes normal solids and fluids no longer applies. Scientists must turn to extreme versions of quantum theory to even begin explaining what is happening. Even then, there are gaps. Some predictions cannot be tested directly. Some equations produce results that seem impossible. Magnetars live in this uncomfortable zone where theory exists, but certainty does not. This is also where Einstein's ideas come under pressure. Einstein's theory of gravity describes how massive objects bend space and time. It has passed every test thrown at it so far, from planetary motion to black holes. Magnetars provide yet another testing ground, but with a unique twist. They do not just have strong gravity, they have gravity combined with the strongest magnetic fields in the universe. Individually, scientists understand strong gravity and strong magnetism fairly well. Together, they become far harder to describe. Near a magnetar, space is curved by gravity, but it is also structured by magnetic forces. Light does not simply follow curved paths, it interacts with magnetism. Empty space itself behaves differently, as if it has physical properties. Some predictions suggest that near a magnetar, the vacuum of space can act like a strange material, splitting light into different paths or changing how radiation moves. These effects are tiny and difficult to observe, but magnetars are one of the few places where they might actually occur. If confirmed, they would represent physics behaving in ways we cannot experience anywhere else. This combination of extreme gravity and extreme magnetism creates a problem that physics has not fully solved. Our best theories of gravity and our best theories of quantum behavior are not fully compatible. They work beautifully on their own, but they do not merge smoothly. Magnetars sit right at that boundary. They force scientists to confront the fact that our understanding of reality is still incomplete. This is not a failure. It is an opportunity. Scientists love studying magnetars precisely because they expose these limits. A theory that only works under gentle conditions is not a complete theory. By studying magnetars, scientists can see where predictions start to break down. They can test which ideas survive extreme environments and which need to be replaced or refined. Magnetars are like natural experiments the universe runs for us. No laboratory on Earth can recreate their conditions. No machine can generate their magnetic fields or densities. Yet nature produces them regularly. By observing them, scientists can gather data that would otherwise be impossible to obtain. Another reason magnetars are so valuable is that they force scientists to think across disciplines. Understanding a magnetar requires knowledge of gravity, electromagnetism, nuclear physics, quantum mechanics, and plasma behavior, all at once. Few objects demand such a complete picture of physics. Studying magnetars pushes scientists to connect ideas that are often treated separately. Magnetars also challenge our intuition about power and stability. In everyday life, stability comes from balance. Things that are too extreme usually fall apart. Magnetars defy this expectation. They are extreme, yet they persist. They crack, flare, and erupt, but they do not immediately destroy themselves. This suggests that the universe has ways of organizing extreme energy without instant collapse. Understanding how this happens could change how we think about energy storage and release on cosmic scales. Perhaps the most profound lesson magnetars teach us is philosophical rather than technical. They show us that reality is not fixed to human comfort. The laws of physics do not care whether environments are familiar or survivable. They apply just as rigorously in places where atoms stretch, space distorts, and energy explodes without warning. Magnetars remind us that what we call normal physics is simply physics under mild conditions. Push those conditions far enough, and the universe reveals deeper layers. Layers where forces we consider secondary become dominant. Layers where space behaves like matter and matter behaves like something unrecognizable. This is why magnetars matter beyond astronomy. They force us to confront the limits of knowledge. They show that even after centuries of scientific progress, there are still places where our understanding fades into uncertainty, and they show that uncertainty is not something to fear, but something to explore. In studying magnetars, scientists are not just trying to catalogue strange stars. They're trying to understand how reality works when it is pushed to extremes. They are asking whether our theories describe the universe completely or only approximately. They are searching for clues that might one day lead to deeper, more unified explanations of nature. Magnetars sit at the edge of that search. They are not answers, they are questions made real. They are reminders that the universe is more flexible, more powerful, and more surprising than our everyday experience suggests. And perhaps that is their greatest contribution. Magnetars teach us humility. They remind us that the universe is not obligated to be simple, gentle, or intuitive. It only has to be consistent. And in those distant, violent, magnetic hearts of dead stars, consistency takes on forms that challenge everything we think we know about reality itself. When scientists first discovered magnetars, they seemed almost mythical, objects so powerful, so violent, and so rare that they felt like cosmic accidents rather than natural outcomes. With only a handful known at the time, it was easy to assume magnetars were extreme exceptions, strange mistakes made by the universe once in a while. But as our instruments improved and our understanding deepened, a bigger and more subtle question emerged. Are magnetars truly unique monsters? Or are they just the visible tips of a much larger hidden population? To answer that, we have to zoom out and look at the universe on a galactic scale. Our galaxy, the Milky Way, contains hundreds of billions of stars. Over its long lifetime, countless massive stars have lived and died. Every one of those deaths left something behind. Some became black holes, many became neutron stars, and a fraction of those neutron stars became magnetars. The key word here is fraction. Magnetars are rare compared to normal neutron stars, but rare in a galaxy this large does not mean few. Based on current estimates, scientists believe there may be tens of thousands of neutron stars in the Milky Way. Among them, magnetars may number in the hundreds or even thousands. Yet so far, we've confirmed only a few dozen. This huge gap between what may exist and what we have actually observed tells us something important. Magnetars are not necessarily uncommon. They are simply very hard to see. The reason we only see a few magnetars is not because they do not exist, but because they do not announce themselves clearly. Magnetars are quiet most of the time. They do not shine brightly in visible light. They do not constantly broadcast radio signals like pulsars. For long stretches of time, a magnetar may look like nothing more than a faint X-ray source, or may be completely invisible to our instruments. If it does not flare, crack, or burst, it stays hidden. This creates a strong observational bias. We tend to discover magnetars only when they misbehave. When a magnetar releases a burst of X-rays or a giant flare of gamma rays, it suddenly becomes impossible to ignore. Satellites detect it instantly. Alerts go out. telescopes turn toward it. For a brief moment, that magnetar steps into the spotlight, but once the outburst fades, it can slip back into obscurity, blending into the background of the galaxy once again. This means there could be many hidden magnetars quietly spinning in the Milky Way right now, completely undetected. They may have already passed their most violent phase. Their magnetic fields may be weakening. Their outburst may be rare or finished altogether. To us, they would look like ordinary neutron stars, or perhaps not appear at all. Another reason magnetars are hard to find is where they live. Many are born in regions thick with gas and dust, the same regions where massive stars form and die. These regions block visible light and even some X-rays. A magnetar buried deep inside such a cloud could flare without us ever seeing it clearly. Its signal might be weakened, scattered, or lost in noise. Our galaxy is not transparent. It hides many of its secrets behind curtains of matter. Distance also plays a role. Magnetars in other galaxies exist, but detecting them is extremely difficult. Only the most powerful flares can be seen from such distances, and even then, they may be mistaken for other phenomena like gamma-ray bursts. This means our confirmed magnetar count is heavily biased toward nearby and active ones. Quiet magnetars in distant galaxies are effectively invisible to us. Understanding how many magnetars exist also requires understanding their lifespan. Magnetars do not stay magnetars forever. Their defining feature, their extreme magnetic field, slowly decays over time. This decay is not gentle. It powers their activity. Starquakes, bursts and flares all drain magnetic energy. As the field weakens, the magnetar becomes less violent. Its outbursts become rarer. Eventually, it may stop flaring altogether. This active phase may last tens of thousands to a few 100,000 years, which is very short by cosmic standards. In the life of a galaxy that is billions of years old, this is the blink of an eye. After that phase ends, the magnetar does not disappear. It simply changes. It becomes a quieter neutron star, difficult to distinguish from others. This quiet death is one of the reasons magnetars feel rare. We are most likely to notice them during their brief, dramatic youth. Once that phase passes, they fade into the background. The galaxy may be full of magnetars that lived fast, burned bright, and then grew silent long before humans ever existed to observe them. In this sense, magnetars are not eternal monsters. They are temporary states. They are neutron stars caught in an extreme phase of their evolution. Some neutron stars may never become magnetars. Some may become magnetars only briefly. Others may spend much of their early lives as magnetars before calming down. The boundaries are not sharp. Nature rarely works in clean categories. This idea changes how we think about magnetars. Instead of seeing them as rare anomalies, we begin to see them as part of a continuum. On one end are ordinary neutron stars with relatively stable magnetic fields. On the other end are magnetars born with magnetic fields so strong that they dominate everything. In between may be objects that share features of both, sometimes flaring, sometimes quiet. Recent discoveries support this idea. Astronomers have found neutron stars that behave like magnetars occasionally, even though they were not classified as magnetars originally. These objects blur the line between categories. They suggest that magnetar-like behavior may be more common than we once thought, just not always extreme enough to catch our attention. From a cosmic perspective, this makes magnetars feel less like freak accidents and more like natural outcomes of stellar evolution under the right conditions. Given enough massive stars, enough supernovae, and enough variation in rotation and magnetic fields, magnetars are bound to appear. They are not mistakes, they are expressions of possibility. Their quiet death also teaches us something profound. Even the most powerful magnetic fields in the universe do not last forever. Energy dissipates, extremes fade. A magnetar that once cracked its own crust and screamed across the galaxy will eventually become silent, spinning quietly in the dark, remembered only by the signals it left behind. In that silence, magnetars join the vast population of stellar remnants that fill the Milky Way. They become part of the unseen structure of the galaxy, contributing mass, gravity, and mystery, but no longer demanding attention. Somewhere, right now, there may be countless such remnants drifting unnoticed, the ashes of ancient violence. So are magnetars unique or common? The answer is both. They are unique in their behavior, their power, and their physics, but they may be common in origin, arising naturally from the death of massive stars under the right conditions. What makes them feel rare is not their existence, but their brief moment of loudness in a universe that is mostly quiet. This perspective changes how we see the cosmos. It reminds us that what we observe is only a snapshot, biased toward the bright and the violent. Beneath that surface lies a hidden population of objects that lived dramatic lives and then faded away. Magnetars are part of that hidden history. They are not just monsters, they are phases. They are stories of intensity followed by silence. And in that pattern, they reflect a deeper truth about the universe itself. Even the most extreme forces rise, peak, and eventually fade, leaving behind quiet remnants drifting through the vast, dark calm of space. When magnetars appear in science fiction, they are usually treated like cosmic villains. Movies and games portray them as glowing monsters that rip planets apart, pull spaceships out of the sky, or trigger instant doomsday events. They are shown as visible, dramatic, and constantly destructive. Everything nearby explodes. Time runs out. Heroes must escape before the magnetar wakes up. It makes for exciting storytelling, but it also creates a very distorted picture of what magnetars really are. The truth is both calmer and far more unsettling. Science fiction exaggerates magnetars in several predictable ways. First, it makes them visually loud. On screen, magnetars glow, pulse, and radiate visible energy like fiery suns. In reality, magnetars are almost invisible. They do not shine brightly in visible light. You would not see one with your eyes unless it was extremely close, and even then, it would not look dramatic. Most of their activity happens in X-rays and gamma rays, forms of light our eyes cannot detect. The most powerful object in the universe looks, to us, like almost nothing at all. Second, movies exaggerate speed and immediacy. In fiction, a magnetar suddenly appears and instantly destroys everything nearby. Reality is slower and more patient. Magnetars form from stars that live for millions of years. Their dangerous effects depend on distance, orientation, and timing. They do not randomly wander through space-hunting planets. They sit where they were born, spinning quietly most of the time. Their violence comes in brief moments, not constant chaos. Third, science fiction often treats magnetars like gravity weapons, similar to black holes. Spaceships are pulled in, planets are torn apart, and matter is crushed instantly. This is simply wrong. Magnetars are not massive enough to destroy planets through gravity unless you're impossibly close. Their danger comes from magnetism and radiation, not from pulling things in. Gravity is not their main weapon. These exaggerations create the impression that magnetars are loud, obvious threats. But what science fiction gets wrong is exactly what makes real magnetars more terrifying. The real danger of magnetars is subtlety. A real magnetar does not announce itself with explosions and glowing light. It can sit quietly for years, completely unnoticed. Then, without warning, it releases an intense burst of radiation that travels across the galaxy. No build-up, no countdown, no visible sign. Just a sudden spike of energy that can affect planets and technology from enormous distances. That silence followed by sudden violence is far more unsettling than anything shown in movies. Another thing science fiction often gets wrong is scale. Films tend to show magnetars destroying entire star systems or ripping galaxies apart. In reality, Magnetars do not work that way. They release enormous energy, but that energy spreads out quickly. They do not wipe out galaxies, they do not cause chain reactions of destruction across space. Their power is intense but localized and brief. The universe absorbs it and continues on. But here is where reality becomes more frightening than fiction. Even though magnetars do not destroy galaxies, they do not need to. Their power is concentrated in a way that can still be devastating under the right conditions. A magnetar flare does not need to crack planets in half to be dangerous. It only needs to disrupt technology, radiation balance, or magnetic environments. For a civilization like ours, dependent on electronics and satellites, that is more than enough. Science fiction also tends to misunderstand how magnetars affect matter. Movies show objects being torn apart violently, flying through space in pieces. In reality, magnetars affect matter in quieter, stranger ways. They distort atoms. They change how particles move. They erase data. They disrupt signals. They damage systems silently. The damage is not always dramatic, but it is deep and systemic. This difference matters because fiction trains us to fear the wrong things. We imagine destruction as explosions and visible chaos. Real magnetars remind us that the most dangerous forces are often invisible. Radiation, magnetic fields, energy that does not burn or explode but interferes, scrambles, and destabilizes. Another major mistake in science fiction is treating magnetars as unpredictable monsters with no rules. In reality, magnetars follow physical laws very strictly. Their behavior is extreme but not random. Their flares are caused by magnetic stress. Their bursts follow patterns. Their spin slows in measurable ways. Scientists can study them, model them, and learn from them. The danger is not that magnetars are magical or unknowable. The danger is that they are perfectly natural. And that is what makes real magnetars more terrifying than fictional ones. They do not need intent. They do not need anger. They do not need purpose. They are not villains. They are just outcomes of physics operating at extreme limits. There is no negotiation with that, no escape scene, no heroic sacrifice that changes the laws of nature. Real magnetars also do not need constant activity to be dangerous. In movies, the threat is always active. In reality, the threat is potential. A magnetar can remain quiet for decades, then release a giant flare that lasts less than a second and still has measurable effects across space. That imbalance between cause and effect, between time spent quiet and damage done, is deeply unsettling. Why then do real magnetars not need fiction to be compelling? Because reality already surpasses imagination. A city-sized object cracking its own surface and releasing more energy in a second than the sun produces in hundreds of thousands of years is not an exaggeration. It is measured fact. A burst of radiation affecting Earth from tens of thousands of light years away is not a plot device. It has happened. Atoms stretching under magnetic force is not artistic license. It is predicted by physics. Fiction often adds explosions because it thinks reality needs help to be dramatic. Magnetars prove the opposite. Reality is already strange enough. There is also a serious danger in misunderstanding science through fiction. When magnetars are portrayed incorrectly, they reinforce false ideas about space, physics, and risk. People begin to think threats come suddenly and visibly, instead of quietly and probabilistically. They imagine the universe as hostile and chaotic, instead of structured and lawful. This can lead to unnecessary fear and a lack of appreciation for how science actually works. Understanding real magnetars replaces fear with awe. It shows us that the universe is not a collection of monsters waiting to destroy us, but a place governed by consistent rules that sometimes produce extreme outcomes. It teaches us that danger depends on context, distance, and probability, not just power. Science fiction is valuable when it inspires curiosity. It becomes harmful when it replaces understanding. Magnetars are a perfect example of why the distinction matters. When we move beyond exaggeration and look at the real physics, magnetars become more than threats. They become teachers. They teach us about the limits of matter, about how energy behaves when compressed, about how forces we consider secondary can dominate under the right conditions. They teach us humility, showing that human intuition breaks down at cosmic scales. And they teach us restraint, reminding us that not everything powerful is destructive. In the end, the most unsettling truth about magnetars is not that they could destroy us. It is that they exist at all, that the universe can naturally produce objects so extreme, so quiet, and so powerful without breaking its own rules. That reality itself, when pushed far enough, becomes stranger than any story we can invent. Science fiction imagines magnetars as monsters. Reality shows us something far more profound. Magnetars are not villains in a cosmic drama. They are proof that the universe is deeper, harsher, and more elegant than our imagination. And once you understand that, you realize they never needed fiction to be terrifying. At first glance, magnetars can feel like isolated monsters, rare and violent objects spinning alone in the darkness. It is easy to think of them as cosmic curiosities, interesting but ultimately unimportant to the bigger picture of the universe. That impression could not be more wrong. Magnetars play a meaningful role in shaping their surroundings, influencing energy flow, matter behavior, and even the long-term evolution of galaxies. They matter not because they're common, but because of how intensely they affect the space around them during their active lives. To understand their role, we must stop thinking of magnetars as single objects and start thinking of them as sources of influence. A magnetar does not exist in isolation. It is embedded in space filled with gas, dust, radiation, and magnetic fields. When a magnetar releases energy, that energy does not vanish. It interacts with everything around it. One of the most important ways magnetars influence their surroundings is through radiation. Magnetars release enormous amounts of high-energy radiation in the form of X-rays and gamma rays. This radiation travels outward at the speed of light and collides with interstellar gas and dust. When it does, it changes that material. Atoms can become ionized, molecules can break apart, energy can be injected into cold regions of space that would otherwise remain calm and inactive. This process may sound destructive, but it is also creative. Energy is one of the key drivers of change in the universe. Regions of space that receive sudden energy injections can heat up, expand, and evolve differently than they would have otherwise. Magnetars contribute to this cosmic energy balance. They help stir the interstellar medium, preventing it from becoming too static or uniform. Magnetars also influence space through magnetism itself. Their magnetic fields extend far beyond their surfaces, shaping the motion of charged particles nearby. These particles spiral along magnetic field lines, creating complex structures of plasma and radiation. This can form glowing nebula-like regions around magnetars, similar in some ways to how pulsars create nebulae, but driven by magnetic energy rather than rotation alone. These interactions affect how energy moves through the galaxy. Magnetars act like sudden sparks in a vast, slow-burning system. They inject energy in bursts rather than steadily, creating irregular patterns that ripple outward. Over long periods, these irregularities contribute to the dynamic, ever-changing nature of galaxies. There is also a chemical impact to consider. High-energy radiation from magnetars can break apart complex molecules in space, but it can also enable new chemical reactions. By ionizing gas and altering energy states, magnetars can influence which molecules form and survive in nearby regions. This affects the chemical evolution of galaxies, including the availability of certain elements and compounds that later become part of new stars and planets. While magnetars are unlikely to directly create life-friendly environments, they play a background role in shaping the raw materials from which future systems form. The universe does not evolve gently. It evolves through cycles of energy release and calm, destruction and rebuilding. Magnetars are part of that cycle. On an even larger scale, magnetars help scientists understand cosmic evolution itself. They represent one possible endpoint in the life of massive stars. By studying magnetars, scientists learn about how stars die, how remnants form, and how extreme conditions arise. This knowledge feeds into broader models of galaxy evolution, star formation rates, and the distribution of stellar remnants across cosmic time. Magnetars also serve as markers of past events. When scientists find a magnetar, they are often also finding evidence of a supernova that occurred thousands or millions of years ago. The magnetar carries information about that explosion, the star that died, and the conditions present at that time. In this way, magnetars act like historical records embedded in space. Another crucial reason magnetars matter is their role in testing the limits of astrophysical models. Many processes in the universe happen too slowly, too gently, or too far away to reveal extreme physics. Magnetars compress extremes into observable moments. They allow scientists to see how matter, energy, and space behave under conditions that would otherwise be unreachable. This makes magnetars essential tools for understanding not just stars, but the fundamental behavior of the universe. Calling magnetars just curiosities misses this point entirely. Curiosities are interesting but optional. Magnetars are informative. They fill gaps in our understanding. They challenge assumptions. They force revisions of theories. Each magnetar discovered adds constraints to what models of stellar death and magnetic field evolution can allow. Magnetars also play a role in the broader ecosystem of compact objects. Alongside black holes and neutron stars, they form part of the population of remnants that dominate the long-term future of galaxies. Long after stars stop forming, these remnants remain. They continue to influence space through gravity, radiation, and occasional outbursts. Magnetars, during their active phase, are among the loudest voices in that future universe. Their place in the cosmic story is therefore not as villains or anomalies, but as transitional figures. They represent moments of extreme expression in the life cycle of matter. A massive star lives fast, dies violently, and leaves behind a magnetar that releases its stored energy in dramatic bursts before fading into quiet obscurity. That arc mirrors the broader rhythm of the universe itself. There is also something deeply symbolic about magnetars. They remind us that the universe is not built only from gentle processes. Calm, stable stars like our Sun are only one part of the picture. The universe also includes objects that crack, flare, and scream briefly before falling silent. Both are necessary. Without extremes, there would be no contrast. Without energy release, there would be no evolution. From a human perspective, magnetars help put our place in the universe into context. They show us that the forces shaping galaxies operate on scales far beyond human control or concern. At the same time, they show us that those forces follow rules that can be understood. The universe is not random chaos. Even its most violent objects behave according to laws that science can uncover. Magnetars matter because they connect many threads of cosmic understanding. They link stellar birth and death. They link magnetism and gravity. They link small size with enormous power. They link silence with sudden violence. And they link theory with observation, forcing scientists to refine their ideas again and again. In the grand story of the universe, magnetars are not the main characters, but they are powerful supporting forces. They appear briefly, make a dramatic impact, and then fade, leaving behind altered environments and new questions. They are reminders that cosmic evolution is not smooth or predictable. It is shaped by rare, intense events that leave lasting imprints. So, when we ask what role magnetars play in the universe, the answer is not simple, but it is clear. They are agents of change. They are laboratories of extreme physics. They are markers of stellar death. They are contributors to the energy balance of galaxies. And they are proof that the universe is capable of producing wonders that challenge our understanding while still obeying its own deep, elegant rules. Magnetars matter not because they threaten us, but because they teach us. They teach us that power does not need size, that influence does not require permanence, and that even in a universe filled with quiet stars and empty space, moments of extreme intensity help shape the story of everything that exists. Magnetars do not end with explosions, they end with silence. And in that silence lies the most important lesson they offer us. Throughout this journey, magnetars have appeared as monsters, as extremes, as objects that crack their own surfaces and scream across the galaxy in bursts of unimaginable power. They bend atoms, overwhelm magnetism, and release more energy in seconds than stars produce in lifetimes. It is natural to feel small when confronted with something like that. It is natural to feel fear. But magnetars are not here to frighten us. They are here to teach us. What magnetars teach us first is the reality of extremes. The universe does not operate only in gentle ranges. It does not stop at what feels comfortable to the human mind. It pushes matter, energy, and space to their limits, and then keeps going. Magnetars show us that nature is capable of storing enormous power quietly, holding it under tension for years, centuries, even millennia, before releasing it in a single moment. This is not chaos. It is structure under pressure. In our daily lives, we associate extremes with failure. Too much force causes collapse. Too much heat causes destruction. Too much pressure causes breaking. Magnetars reveal a deeper truth. Extremes are not mistakes. They are part of how the universe explores its own boundaries. They are how reality tests what it can become. Magnetars also force us to confront our place in the universe, honestly. We live on a small planet, orbiting an ordinary star in a quiet region of a vast galaxy. Most of the time, that feels abstract. Magnetars make it real. They remind us that the universe is not designed around us. It does not scale to our fears or our hopes. Its forces operate on levels that dwarf our civilizations, our technologies, and even our imagination. And yet, despite that smallness, we are not insignificant. This is the paradox magnetars reveal. We are tiny in scale, but capable of understanding. A city-sized object, thousands of light years away, releases a burst of energy, and fragile instruments built by human hands detect it. Equations written by human minds describe it. Curiosity drives us to study it. We cannot control magnetars. We cannot survive near them, but we can comprehend them. That is extraordinary. Understanding monsters makes us wiser, not weaker. Fear thrives in ignorance. When something feels unknowable, it becomes terrifying. But when we learn how it works, when we understand its limits and rules, fear gives way to respect. Magnetars stop being cosmic threats and become cosmic teachers. They show us how energy behaves when compressed, how matter reacts under extreme stress, how invisible forces like magnetism can dominate reality. They also teach us restraint. Magnetars remind us that power does not equal intention. The universe is not hostile. It is indifferent. Magnetars do not rage. They do not target. They do not choose. They exist because physics allows them to exist. This distinction matters. When we stop assigning human emotions to cosmic objects, we begin to see the universe more clearly. Curiosity is the correct response to this clarity. Throughout history, humanity has faced things that once looked like monsters. Storms, eclipses, volcanoes, diseases. At first, they inspired fear and myth. Over time, understanding replaced superstition. The monsters did not disappear, but our relationship with them changed. We learned how to prepare, how to predict, how to respect without panicking. Magnetars are part of that same story, playing out on a cosmic scale. Choosing curiosity over fear does not make the universe safer. It makes us stronger within it. There is also something deeply humbling about magnetars that goes beyond science. They show us that the universe does not need us to be dramatic. It creates wonders without witnesses. Magnetars were cracking and flaring billions of years before humans existed, and they will continue long after we are gone. Our discovery of them does not change their behavior. It changes us. That realization invites reflection. We often measure importance by visibility and longevity. Magnetars challenge that. They are small, rare, and short-lived compared to stars and galaxies. And yet, during their brief, active lives, they dominate their environments and reshape understanding. This echoes something profoundly human. Impact does not require permanence. Influence does not require size. Magnetars burn intensely, then fade quietly. Their energy disperses into space. Their magnetic fields weaken. Eventually, they become silent neutron stars, drifting unnoticed through the galaxy. No final explosion, no grand ending, just a gradual return to quiet. There is beauty in that. It mirrors the larger rhythm of the universe. Creation, intensity, dissipation, silence, nothing is wasted. Energy spreads, matter rearranges. The universe moves forward without conclusions, only transitions. Magnetars do not give us neat endings or final answers. They give us moments of clarity followed by deeper questions. And that is exactly how science works. At the end of this story, we do not arrive at certainty. We arrive at wonder. We see that reality is far richer than our instincts suggest, that the universe contains forces so extreme they break our intuition, yet remain governed by elegant laws, that even the most violent objects are part of a larger balance. Magnetars do not exist to threaten us. They exist to remind us that the universe is capable of far more than comfort. They remind us that knowledge is not about control, but about understanding. That wisdom is not about eliminating fear, but about knowing when fear is unnecessary. When you look up at the night sky after learning about magnetars, nothing changes visually. The stars look the same. The darkness remains quiet, but something shifts internally. You begin to understand that beneath that calm surface lies a universe alive with extremes, silent power, and unseen drama. And yet, here we are, able to ask questions about it. That is the real ending. Not a warning, not a conclusion, but an invitation. An invitation to keep looking, to keep learning, to choose curiosity when fear feels easier, to accept our smallness without surrendering our wonder. Magnetars do not give us answers about meaning or destiny. They give us something better. Perspective. And in a universe this vast, that may be the most powerful gift of all.